Hello, this is Mr. Christensen. We are going to solve some kinematics problems in this video. First, water drips from rest from a leaf that is 20 meters above the ground. Neglecting air resistance, what is the speed of each water drop when it hits the ground? This is an interesting problem. It requires you to have a piece of knowledge that is not explicitly stated in the problem. But we're going to start by picking out the things that are explicitly stated. First, from rest means our Vx0 is 0 meters per second. 20 meters above the ground gives us a displacement of 20 meters. Neglecting air resistance, what is the speed? Meaning Vx is our unknown when it hits the ground. The piece of information that you're required to infer from the problem is the fact that since this is falling, it's accelerating under the acceleration due to gravity, which is 9.8 meters per second squared. So this problem is, well, really all of these problems require you to choose the correct equation. This one is a little bit easier in my opinion because it does not have one particular piece of information that's a dead giveaway as to what equation you're going to use. And that is the fact that it does not provide you or ask you to solve for time. So when time is not provided, we only have one equation that doesn't contain time, and that happens to be Vx squared equals Vx0 squared plus 2a x minus x0, which we know is just the representation of delta x. So once we have this equation, we can go ahead and fill it in. Vx is our unknown, so we're going to leave it alone, equals Vx0, 0 squared, plus 2, 9.8, and then our delta x is 20. So if we do that out, we end up with Vx squared equals 392. And then the final step would be to take the square root, and you end up with a Vx of 19.8 meters per second. Okay, next. What do we got? Well, we have another problem that involves gravity. What is the maximum height that will be reached by a stone thrown straight up with an initial speed of 35 meters per second? So let's go ahead and identify what we need and what we have. What is the maximum height? Meaning displacement is our unknown. A stone thrown straight up, which is indicating that we are going to be accelerating under gravity, 9.8 meters per second squared, and an initial speed of 35, meaning Vx0 equals 35 meters per second. So this problem also requires you to have a little bit of intuition, a little bit of physics knowledge about what exactly is going on here. And that is when something reaches its maximum height, it is going to have a velocity of 0. So if you think about it, what's happening is you throw it straight up, it decelerates on its way up, it stops for just a tiny fraction of an instant, and then starts falling back down in the opposite direction. So we're going to go ahead and identify again, this is a problem that does not require time. So we will go and we will pick out our Vx squared equals Vx0 squared plus 2a delta x, or well, x minus x0. And now we can plug and chug. Vx is 0 squared equals Vx0, 35 squared, plus 2 times 9.8 times delta x. All right. And for this problem, we are going to need to slap a negative on that 9.8 since it is an acceleration downward, and we are throwing it upwards. So we get 0 equals 35 squared, which is 1225 plus a negative 9.8 times 2, negative 19.6 delta x. Subtract this over. We end up with negative 1225 equals negative 19.6 times delta x. Divide by negative 19.6. And you end up with a delta x of 62.5 meters. And there's your answer. Our next problem. We have a multi-part problem. A ball is shot straight up from the surface of the Earth with an initial speed of 19.6 meters per second. Neglect any effects due to air resistance. This is almost identical to the previous problem. So that means we have a initial speed, Vx0, of 19.6 meters per second. We have a Vx final of 0 meters per second. We have an acceleration of negative 9.8 meters per second squared. So what we're going to do is we're going to use our Vx squared equals Vx0 squared plus 2a delta x. I'm just going to take the shortcut. And I'm going to go ahead and write down here. We'll come back to this slide at some point so we can do number 13. But we get Vx is 0 squared equals 19.6 squared plus 2 negative 9.8 times delta x. So 19.6 squared equals, so 0 equals 384.16, and that is minus 19.6 delta x. So if we subtract over 384.16, we have negative 384.16 equals negative 19.6 delta x. Divide by negative 19.6. And we have a delta x of, again, which is interesting, getting a lot of 19.6s, 19.6 meters. Okay, so there's your answer to the first part. Now let's go back and erase some stuff so that we can solve the second part of this problem. How much time elapses between the throwing of the ball and its return to the original launch point? So if we're asked how much time, that means delta t is our unknown. We still have a Vx0, a Vx, and an A. So what we can do for this one is we can go ahead and say, okay, Vx equals Vx0 plus a delta t. And now we have to be careful and understand that if we're using the information provided in number 12 that we have listed, we're only finding the time that it takes to get to the top position, not the total time that it takes to go up and then down. The easy thing is we basically just double the time that we get because it takes just as much time to go up as it does to go down. So let's go ahead and do that. We have Vx equals Vx0 plus a delta t, and if we fill that in, we have 0 equals 19.6 plus negative 9.8 times delta t. If we continue on, we end up with negative 19.6 equals negative 9.8 delta t. Divide by negative 9.8. You end up with a delta t of 2 seconds. So that is for the up portion, times 2 equals 4 seconds total for the up and down portions. So there's that answer. Okay. A car is moving 15 meters per second east when it begins an acceleration towards the east of 3 meters per second squared. How long will it take this car to reach a velocity of 30 meters per second east? How far will the car travel during this time? So let's go ahead and identify what we're given. So 15 meters per second east, that's our Vx0, 15 meters per second. An acceleration of 3 meters per second squared. And a final velocity, meaning a Vx of 30. Cool, cool. So we have how long is the first part of this, meaning delta t equals blah. For this one, it's actually going to be pretty straightforward. We can go ahead and use Vx equals Vx0 plus a delta t. So our Vx is 30, our Vx0 is 15, our acceleration is 3, and then delta t. So subtract 15, you end up with 15 equals 3 delta t. Divide by 3 on both sides. You get a time of 5 seconds. There's your answer for the first part. Go back. And what we want to know is how far will it go is the second piece. So still same information, but now we want to know how far it's going to go. So the question is delta x is our unknown. Well, what we have is we now know that the time is 5 seconds. We have a couple of ways of doing this problem. I'm going to choose one particular way, and that would be, what am I going to do? I'm going to do x equals x0 plus vx0 t plus 1/2 a t squared. Now when we subtract over x0, we get x minus x0, which we know is delta x, which is what we're looking for, so that's good. So we end up with delta x equals vx0t. Vx0 is 15 times the time of 5 seconds, plus 1/2 acceleration is 3 times t5 squared. Our delta x is 15 times 5, 75 meters, plus 1/2 of 3 times 5 squared, 25 times 3 divided by 2, 37.5. Add those together, you get a delta x of 112.5 meters. And there's your answer. All right. During a 10-second period, a car has an average velocity of 25 meters per second and an acceleration of 2 meters per second squared. Determine the initial and final velocities of the car. This is a particularly interesting question. So 10 seconds is our time an average velocity of 25 meters per second. So V average is 25 meters per second. And an acceleration of 2 meters per second squared. So what we're going to do is we are going to identify the fact that V average is Vx0 plus Vx over 2. Okay, that's the average. You have two terms, add them together, divide by 2, that gives you a V average. So if that equals, not 15, 25 meters per second, we can then multiply by 2. We get that Vx0 plus Vx equals 50 meters per second, which means that Vx equals 50 minus Vx0. And this is very helpful because we know that the definition of acceleration is delta V over delta t, which is Vx minus Vx0 over delta t. So if we want the initial and final velocities, we need to say that if we multiply by delta t, we end up with Vx minus Vx0 equals a delta t. We have just said that Vx is equal to 50 minus Vx0, so we can actually substitute that right in there. So Vx is 50 minus Vx0 minus Vx0 equals a delta t. So 50 minus 2 Vx0 equals an acceleration of 2 times a time of 10. So 50 minus 2 Vx0 equals 20. Subtract, not 20, 50. Subtract 50. And we have negative 2 Vx0 equals negative 30. Divide by negative 2, divide by negative 2. Vx0 equals 15 meters per second. That's the first part of your answer. Then we have just solved earlier up here again that Vx is 50 minus Vx0. So Vx is 50 minus 15, giving you a Vx of 50 minus 15, oh boy, 35 meters per second. And there is the second piece of your answer. All right, a kangaroo jumps vertically to a height of 2.7 meters. How long will it be in the air before returning to Earth? Great question. Jumping vertically, okay, straight up means acceleration of negative 9.8 meters per second squared to a height of 2.7 meters. Delta x is 2.7 meters. How long will it be in the air means delta t is our unknown before returning to Earth. So what we're going to do is we're going to identify, okay, the V, hold on, Vx, yes, Vx equals 0 meters per second because at the top of its jump, as we previously discussed, the height of the okay, hold on. At the top of the jump, the final velocity is going to be 0. Again, because we're traveling up, we pause for an instant, then we start coming back down. So if we can use this information right here to calculate the initial velocity, that means we can then use that to calculate time. So based on what we have here, we can use Vx squared equals Vx0 squared plus 2a delta x. And we can go ahead and solve for the Vx0, which we will then use to find delta t. So Vx squared 0 squared equals Vx0 squared plus 2 times negative 9.8 times delta x, which is 2.7. We can subtract over Vx0 squared, so we end up with negative Vx0 squared equals 2 times negative 9.8 times 2.7 equals a negative 52.92, and then if we divide by negative 1, we just get rid of those negative signs, so I can go ahead and just get rid of those, and then take the square root. Vx0 is 7.27 meters per second. So with this information, we can then go ahead and say, all right, I know that Vx equals Vx0 plus a delta t. So Vx being 0, Vx0 we just found 7.27 plus negative 9.8 delta t. Subtract over 7.27, so negative 7.27 equals negative 9.8 delta t. Divide by negative 9.8. Delta t equals 0.74 seconds. Now, I know that is different from the answer key. Why is that? Because we have just calculated the time it takes to jump straight up. So this is up. So times 2 to give us delta t total, which is 1.5 seconds. Awesome. There's our final answer. And here we go. A stone is thrown vertically upward with a speed of 12 meters per second from the edge of a cliff, 75 meters high. How much later does it reach the bottom of the cliff? What is its speed just before it hits the ground? And what is the total distance that the stone travels? So here's what we need to do. Part A is doable, certainly. Here's what we need to do. So we are going to identify that we're throwing vertically upward, meaning A is negative 9.8 meters per second squared. Our initial speed, Vx0, is a positive 12 meters per second. And its initial position, x, so here's where we're going to actually use initial and final position. Its initial position is 75 meters. What the other piece of information is that reaching the bottom of the cliff means our final position is going to be 0 meters. So if we're going to solve this, we need, we need time. So we need delta t. Okay. Here's what we can use. We can use x equals x0 plus Vx0t plus 1/2 a t squared. I'm just kidding. We can't use that because that gives us two variables. Although we could use the quadratic equation. But who wants to do that? What are we going to do? We have a Vx0 and x0. Well, what we can do is we can actually solve this in a couple of ways. We can determine how much time it takes. So here's our physical position. We throw it up and then it falls straight down. So what we could do is we could go ahead and solve for this time, determine the velocity that it's moving when it hits this point right here, and then add those times together. So why don't we go ahead and do that? So our time that it's going to take to go straight up and reach the peak of its height is going to be, we're going to use Vx equals Vx0 plus 2a delta x. So our V final is again going to be 0, and that equals, oh, that's going to be squared, sorry. So our, nope, that's again, I'm sorry, hold on. Boop. Vx equals Vx0 plus a delta t. My apologies. My apologies. All right, so Vx is going to be 0 because we're reaching the top, equals Vx0 12 meters per second plus a negative 9.8 meters per second squared times delta t. So we get negative 12 equals negative 9.8 delta t. Divide. We end up with a delta t of 12 divided by 9.8 equals 1.22, not meters, seconds. And so that is the up time times 2 will equal 2.44 seconds for the first piece. Okay, first piece. And that is the, again, if this is our cliff, that is the up and down before it reaches this point, time. So that means that the first piece of the time is 2.44 seconds. Then we are going to say, okay, I know that at this point, once it reaches, so here's our cliff, we're going up and down. Once it reaches the height of the cliff, it's going to be going the exact same magnitude of the speed that it was being thrown up at, except now it's going to be negative. So it's going to have negative 12 meters per second. It's going to be its velocity at that point. So if we want to calculate the time it's going to take for this piece right here to make it all the way to the ground, we are going to need, what do we need? We can calculate, okay, well we can use this. We can use this, but if we start with a Vx0 of negative 12, we're going to need to calculate the Vx. So in order to do that, we're going to use Vx squared equals Vx0 squared plus 2a delta x, where in this case our Vx is our unknown. Our Vx0 is negative 12 squared plus 2 negative 9.8 delta x is 75 meters. So if we do this out, we get 144 plus 2 times 9.8 times 75. So a negative, 2 times 9.8 times 75, calculator, plus a negative 1,470. Add those together, and again, this is a negative 75 meters. So that means we're going to add those. Yes, okay. Yeah. So we add those together. 144 equals, so Vx squared equals 1,614. Square root that, you get a Vx of 1,614, no, square root of that equals, okay, so 40.17 meters per second. With this information, we can now use Vx equals Vx0 plus a delta t. We can go ahead and say our Vx is negative 40.17. Again, it's negative because it's moving down. Equals negative 12 plus negative 9.8 delta t. So if we add this over, we end up with a 28.17 equals 9.8. I dropped the negatives because we have this negative and this negative canceling each other out, times delta t, divide, and we end up with a delta t of 2.87. That's awesome. What does that tell us? That tells us the time that it takes from here to here. So our delta t2 equals 2.87. So if we add those two together, we end up with a whopping total time of 5.32. Well, comes out to 3149, so we're going to round up. Seconds total. Awesome. And interestingly, we actually already calculated the speed just before it hits the ground. That was speed just before it hits the ground was right here, 40.17. And the total distance that the stone travels, we can still calculate. So distance meaning total path. We can go ahead and do that by calculating, so we're going to go back here, the total distance that the stone travels. We are going to use, so we know that this is, right here, this is 75 meters. What we need to know is this part right here. So that is going to be, we're going to use Vx squared equals Vx0 squared plus 2a delta x, and we're just going to solve it for the way up. So if we know that distance, then we can just multiply it by 2, add 75, and we're good to go. So our final velocity is going to be 0. Our initial velocity is going to be 12 plus 2a negative 9.8 delta x. Squared on there, so 144 equals negative 144 equals negative 19.6 delta x. So that delta x is 144 divided by 9.8. Nope, not 9.8. 144 divided by 19.6. Thank you very much. 7.34 meters for the way up times 2 equals a total of 14.7-ish meters total, plus a 75 meters equals, I'm writing up here, so sorry, an 89 point, call it 7 meters. And there is your total distance traveled. And there's that. So, and now we have the AP test questions. So let's go through those. So a small cart is rolling freely on an inclined ramp with a constant acceleration of a positive 0.5 meters per second squared in the negative x direction. Oh, no, I'm sorry. Constant acceleration of 0.5 meters per second squared in the negative direction. At time t equals 0, the cart has a velocity of 2 meters per second in the positive x direction. So we've got a negative acceleration and a positive initial velocity. If the cart never leaves the ramp, which of the following statements correctly describes the motion of the cart at time t greater than 5? Greater than 5. So in 5 seconds, we know that Vx equals Vx0 plus A delta t. So our Vx, so our V final is going to be 2 plus negative 0.5 times 5. So that's a Vx equals 2 minus, and then 0.5 times 5 is a minus 2.5, giving us a negative 0.5 meters per second. So what does that tell us? That means that the cart is traveling in the negative x direction. If it is traveling in the negative x direction with a negative acceleration, that means D, the cart is traveling in the negative x direction and is speeding up. All right. An object's velocity v as a function of time t is given in the graph above. Which of the following statements is true about the motion of the object? So, let's go through these and figure it out. The object is not moving from t equals 4 seconds to 10 seconds. So, if this is 2, 4, 6, 8, 10, so velocity, the value of the velocity at from 4 to 10 seconds is 10 meters per second, so that is a no. The object's initial and final positions are the same. So in order to calculate the initial and final position, we need the area under the curve to calculate displacement. That means we need to do, so from here to here is 2, 4, 6 times 10 is 60, and then 2, 4 times 10 is 40, times 2 is, am I an idiot? No, I'm not. So 1/2 base times height, okay, that's 80. So this total is going to be 140 meters. In here, we have 2, 4, 6, 8, 10, 12, 14, 16, 18 times negative 5, giving us a total of negative 90, right? Yeah. And then we have 2, 4 times negative 5, which is a negative 20, giving us negative 110. So 140 meters positive, a negative 110 meters negative, meaning the initial and final positions are not the same. All right, let's go through that and just erase. The object is slowing down from t equals 14 seconds to 16 seconds. So 10, 12, 14. So our initial position is here, and then 16 seconds is here. Here we have a negative slope. So a negative slope means a negative acceleration. So we are going to say that C is the true statement. Now, what about D? The average acceleration from 0 to 4 seconds is different from the acceleration from 34 to 36 seconds. So that means we're comparing this and this. So this is to 4 and 10, so a rise of 10 over a run of 4. This is a rise of 5 over a run of 2. So that means these are the same, meaning that this is not true. C is the only true statement. Okay, a kitten sits in a lightweight basket near the edge of a table. If we knock the basket off the table, the kitten rolls, turns, kicks, and catches the basket in its claws. We land on the floor. What is the acceleration of the kitten basket system while the kitten and basket are in midair? And that is going to be, the acceleration is directed downward with equal to g because the system is a projectile. So we need to picture the kitten basket system. Basket, 1, 2, 3, 4, kitten, boop, boop. All right, so if we put a bubble around the whole kitten basket system, it doesn't matter what's happening in here. This doesn't matter at all. You can be rotating, flipping, pushing, whatever. The center of mass of the kitten basket system, somewhere in here, will always be accelerating downward at g. All right. The graph shows a velocity v as a function of time t. For a 0.5 kilogram object traveling in a straight line, the graph has 3 segments. A rope exerts a constant force along its direction of motion the whole time. During segment 2 only, a frictional force is also exerted on the object. So, force F, so when force F, T, is the only force acting on the object, that's what I just circled in green, and where force of friction acts, that's what I just circled in red. So, which of the following correctly ranks the displacement, delta x, for the 3 segments of the object's motion? So, as we learned, the displacement is the area under the curve. So I'm going to split this up into those sections. So the area under the curve would be a rise of, so the area would be base 2 times height 4 times 1/2, giving us a displacement of 4. This is going to be 1, 2, so 2 plus 2 plus a base of 2 and a height of 3 times 1/2, because it's a triangle. We're going to get 2 plus 3 equals 5. And then we have 1, 2, so 2 plus a base of 2 and a height of 1, 2, 3, 4. So 4 times 2 times 1/2 is 2 plus 4 equals 6. So that means delta x3 is greater than delta x2, greater than delta x1, greater than 0. A is the correct answer. Finally, a lion is running at a constant speed towards a gazelle that is standing still, shown in the figure above. After several seconds, the gazelle notices the lion and accelerates directly towards him, hoping to pass the lion and force him to reverse direction. As the gazelle accelerates towards and past the lion changes direction and accelerates in pursuit of the gazelle. The lion and gazelle eventually reach constant but different speeds. Which of the following set of graphs shows a reasonable explanation of the velocities of the lion and the gazelle as functions of time? Okay, let's work with the lion first. So, first of all, the lion is moving in the negative direction. That means it starts with a negative velocity. So these two are out because they start with a positive velocity. So we need to start with negative velocity. So that means we're only left with A and B. A and B. So after several seconds, the gazelle notices the lion. That means for several seconds, the gazelle has a velocity v equals 0, which is this graph, meaning A is the correct answer. And that is it. Please email me at mchristiansen@baypath.net if you have any questions, and I hope this was all very useful to you.